All right, so U substitution, hopefully you've gotten used to it now, the 6-step process, substituting in for U. That's how it works for indefinite integrals. How it works for definite integrals is a little bit different. So I'm going to show you 2 different ways of doing this. There's the way the textbook does it, and then there's another way that I do it. And it's totally up to you, but you do have to pick one of these 2 different ways of doing it. Okay? So let's look at this. We're looking at evaluating the integral from 0 to 1 of x times x squared plus 1 quantity cubed with respect to x. So again, the only difference here is we have limits of integration. So what would we do if we saw this problem? Well, again, one thing that we could do is distribute it all out, but that would take way too long. It'd be way too ugly. We're not going to do that. So let's go ahead and do step 1 here, which is define u. So we're going to let u equal x squared plus 1. Step 2, same thing, differentiate both sides. Du dx is going to be equal to the derivative of x squared plus 1, which is simply 2x. Step 3 is solve for dx. We would have dx would equal du over 2x. So here's where things get a little bit different. Step 4 is substituting it in. When we substitute it in, we are using u's instead of x's. So what we have to be careful of here is when we write those limits of integration, we can't simply come in here and say 0 and 1, because that would infer that this is in terms of u's. So what we need to do is not only change our variables x's in terms of u's, but we also need to change our limits of integration. So how do we change our limits of integration? Here's how we're going to do it. Look at the different values. So consider what we want to find out. We know what x is, and we want to find out what u is. So u is x squared plus 1, right? So we need to look at our limits of integration. Our upper limit of integration was 1. So u would be 1 squared plus 1, which is 2. Our lower limit of integration would be 0. So that would be 0 squared plus 1, which is a 1. So our 2 limits of integration, if we changed our limits of integration, would now be 1 and 2 instead of 0 and 1. So it's very, very, very important when you use definite integrations. You must change the limits of integration. Okay. Now that's one of the techniques, but this is the technique that's taught to you in the book, so that's what I want to show you. The other one would be writing x equals 0 and x equals 1 and doing the entire problem that way. Okay, it is just as easy to do it the other way, but I want to keep it consistent with the book, so this is the method that I'm going to show you. So let's go into step 4 to rewriting it. Again, we're solving for dx, substituting in for dx. We're also substituting in for u. But then we also had to substitute in for those limits of integration. So never forget those limits, substituting in those limits of integration. And this is going to give you a nice little trick. So let's look at this. This would be the integral of x. Then instead of x squared plus 1 quantity cubed, that would be u cubed. And then instead of dx, you have du over 2x. Again, the x's simplify. We do see that we have a constant multiple of 1/2. So this is going to be 1/2 times the integral from 1 to 2 of u cubed du. I'm about to show you the beauty of swapping those limits of integration. So let's go ahead and move on to example 5, and let's integrate. This would be 1/2 times the integral of u cubed, which is u to the 4th over 4. And then this is evaluated from u equals 1 to 2. So this is really 1/8 times u to the 4th evaluated from 1 to 2. So here's the beautiful thing. If we swap the limits of integration, remember these numbers are now in terms of u, not x's. So I do not need to back substitute for u in this case. So this would be equal to 1/8 times 2 to the 4th, 1/8 times 2 to the 4th minus 1 to the 4th. And when I do that, I end up with a fraction of, let's see what you get. I'm getting a total of 15/8. Please double check my math there. Okay. So let me show you a second way of doing it. The second way of doing it would have been extremely, extremely similar. But the difference is that you leave the integration limits in terms of x's. And if you do that, here's what you must do. When you're rewriting the integral, you must write x equals 0 and x equals 2, because that's the variable, or sorry, x equals 1 was the original problem, right? You would still end up with the 1/2 and you have the u cubed du, but notice I'm writing x equals each one of these times, and that's really, really important for you to do, okay? So this is going to be 1/2 times the integral of u cubed is u to the 4th over 4. And then, of course, it's plus c, but this is from x equals 0 to x equals 1. So this is the 1/8 u to the 4th from x equals 0 to x equals 1. Now I would back substitute, just like I did with my indefinite integration, and this would be x squared plus 1. This would be evaluated from 0 to 1. And this is where I'd figure it out, that it's 1/8 times, and I'd plug it in, and I'd have 1 squared plus 1 minus 0 squared plus 1. And that's where I get my value of 50, this entire thing is raised to the 4th power. Can't forget that. And so that would be 2 to the 4th minus 1 to the 4th, which would be 16 minus 1, which is 15/8, which gives us the exact same answer right there. Okay? So you can choose option 1, which is the way the textbook does it, or option 2, which is another way that I do it. The only key is I like option 2 in the sense that it's no different from indefinite integral except the last step. The only difference is you must remember to write x equals on every single one of those steps. If you do not write x equals on those steps, I have to infer that it's u equals, and that's not correct. So please don't do that. Either pick option 1, which is what the textbook does, changing the limits of integration, or process 2, which would just be writing x equals. Your choice. I don't care which method you do. Okay, so let's look at this last integral, integral 9, or example 9 here. Evaluate the definite integral, the integral from 1 to 5 of x over the square root of 2x minus 1. So what do? Again, we're going to start off with defining our u. So we're going to let u equal 2x minus 1, the inside of the function. Step 2, find the derivative of both sides. So I have du dx equals the derivative of 2x minus 1, which is simply 2. Step 3 is solve for dx. So in this case, dx would equal du over 2. So what do? I rewrite my integral. So that's step 4. I have to be really careful, though. I have to remember I have to solve for what u would equal. So let's do that now. We know that u equals 2x minus 1, and I have to look at my x values. I'm going to change out my limits of integration here. If I have an upper limit of 5, that would be 2 times 5 minus 1, which would be 9. So that's my new limit. My lower limit of integration was 1, so this would be 2 times 1 minus 1, which is still the number 1. So that's my new lower limit of integration. So when I integrate this, now in terms of u, my limits are going to be from 1 to 9. I have x, and then instead of over the square root of 2x minus 1, I'm going to write that as a u to the negative 1/2. And then dx I have is du over 2. Now if you realize, we still have that x there, and so something's going wrong, right? So the idea is we have to go back and resolve u in terms of x. So if we know u equals 2x minus 1, add 1 to both sides, I'd have u plus 1 equals 2x. Divide everything by 2, and I'd have u plus 1 over 2 equals x. So that's what I'm going to substitute in for x. So this is going to turn into the integral from 1 to 9 of, instead of x, I'd have u plus 1 all over 2. And then I still have the u to the negative 1/2. And then I have the du over 2. So when I do that, I need to pull out the constant multiple, which would be a 1/4. I have the integral from 1 to 9 of, well, let's do our multiplication. U times u to the negative 1/2. You add the exponents because it's multiplication, so that'd be u to the 1/2. And then 1 times u to the negative half would be plus u to the negative 1/2. And then all of this is du. Now we're able to integrate both of these, so this would be 1/4 u to the 1/2 integrated would be u to the 3/2 over 3/2, which is the same as multiplying it by the reciprocal of 2/3. The integral of u to the negative 1/2 would be u to the positive 1/2 over 1/2, which is the same thing as multiplying it by 2. And then remember, we have to still evaluate this from 1 to 9. Again, the beauty of this is we no longer need to back substitute for u because we changed our limits of integration. So this would be, this was step 5 right there, or step 5 right here is where I actually integrated. Okay, now I'm moving on to step 6, which is just evaluate it. So this is going to be a total of 1/4 times 2/3 times 9 to the 3/2 plus 2 times 9 to the 1/2. So that's what I get when I plug in 9. And then, of course, I need to subtract off, plugging in the number 1. So that'd be 2/3 times 1 to the 3/2 plus 2 times 1 raised to the 1/2. Plug that all into your calculator and let's see what you get. I'm getting a total of 16/3. And please let me know what you got.